Why are quantum qubit measurements probabilistic? Imagine flipping a coin that can land on heads or tails, but you never know which until it actually lands. Now, picture a tiny quantum that can be in both states at once until you look. That's what happens with qubits in quantum computing. Unlike regular bits that are either 0 or 1, qubits can be in a superposition of both states simultaneously. This superposition is described by a wavefunction, which is like a mathematical recipe that tells us the chances of finding the qubit in each state when we measure it. The wavefunction contains what are called probability amplitudes. These are complex numbers that encode how likely it is to observe the qubit as 0 or 1. When you measure a qubit, the superposition collapses suddenly and randomly into one of these definite states. The chance of it collapsing into 0 is the square of the magnitude of the amplitude for 0, and the chance of it collapsing into 1 is the square of the amplitude for 1. This randomness is built into the very nature of quantum mechanics. Think of the wave function like a wave in the ocean. When waves interfere, they can amplify or cancel each other out. Similarly, the probability amplitudes can interfere constructively or destructively, affecting the likelihood of each measurement outcome. This interference is what makes quantum computers so powerful. They can process many possibilities at once, thanks to these wave-like properties. Another key point is that how you measure a qubit matters. If you choose to measure in a different basis, the superposition changes how the wave function is projected onto the measurement states. This means the probabilities of getting 0 or 1 can shift depending on your measurement setup. Because measurement results are not predetermined but instead probabilistic, quantum algorithms often need to be run many times. By repeating the process and analyzing the results statistically, scientists can find the most likely answer. This probabilistic behavior is what makes quantum computing different from classical computing, where outcomes are always predictable if you know the initial conditions. In essence, the randomness in qubit measurement comes from the core principles of quantum mechanics: superposition, wavefunction collapse, and interference. These features allow quantum computers to explore many solutions at once, making them incredibly powerful for certain types of problems. So, the next time you hear about quantum computing, remember that its magic lies in this fundamental unpredictability that actually opens new doors to solving complex puzzles.